right, today we are going to continue talking about our analytic strategies for limits. We're going to talk about a theorem, and then we're going to talk about evaluating some trigonometric limits. Okay. Yay, trig. So here is our theorem. This is called the squeeze theorem. Sometimes you may hear it called the sandwich theorem. Okay? This is saying if I have three functions where the middle function is in between the two other functions, or equal to, okay? Then, if I take the limit of the outside functions and it equals L, then the meat of the sandwich, whatever squeezed in the middle, is going to have the same limit.
So both the limits of the outsides are so the limits of the outside are the same, then the limit of the inside is also the same.
Is that, okay? There's going to be times where we may not be able to evaluate a limit. So we can find, like here I'll show you this picture, okay? This blue function is H, this pink function is G. So notice how function F is sandwiched in between, and they come and they actually meet right here.
So it's kind of just saying that if one's in between the others and they're all equal to each other, then this one's fine, where they're all the same.
The limit, yes. Yes. Obviously, the sandwich theorem would not work right here because your limits for G and H would not be the same. Your limits for G and H need to be the same at a point, so like here, right? And then that is also going to be the limit for F. Yes.
How would you know by looking at the equations that G is greater than or equal to F and F is greater than or equal to H?
You would need to have knowledge of their graphs.
Okay.
Cool. Okay. But basically, you know, we're squeezing function F in between two functions strategically so that we're looking at the point where they all three meet, right? And that's where we're going to be evaluating that limit. Okay. Now, this is something that we talk about, and it doesn't really get talked about very much, but you need to know it so when I reference it, you understand what I'm talking about. Okay? It's not a strategy that is used very often, okay? Because we have so many other strategies to help us. Okay? So, yes.
Does this work if it doesn't like necessarily F were to like not have any point where C is? Then would
As in no point, like a hole?
like a gap.
Well, if there's no domain there, then we can't evaluate the limit, right? Okay. So, we're going to, we want to find the limit as x approaches 0 of x sine of 1 over x. Now, what's the problem with trying to evaluate this limit? Okay, it makes the denominator 0, and there's really nothing algebraically we can do for 1 over x. So I'd like you to get your calculators out, and I want you to graph x times the sine of 1 over x. Make sure you are in radians.
Oh, that's weird.
Dang it.
Using
Oscillation.
Okay, so what's happening?
Oscillation.
it's easy.
It's oscillating.
Sure it will.
Doesn't it just kind of dip down once?
Mine's
Mine goes once.
mine is mine like 52.
I
Is
zoom.
your window different?
I didn't zoom fit.
Zoom fit, huh?
Change the window. My window's negative
Because
1.
you're in
one,
Zoom
one,
standard, right?
negative 1.
Mm-hmm.
Well, my Zoom standard, I should have.
If my window is negative 1, it's like a 1 block.
By doing zoom fit,
Yeah.
it is negative 15
That's right.
to 15 for x, and 0.001 to 0.99
Ah,
for y.
you're so smart.
Oh, shoot.
That's
My
right.
Now my graph looks like yours.
Hmm.
Okay, that's
Well,
not,
Batman.
that's not
Awesome.
on the thing.
I zoomed into 1 by, or this is,
One by one, by one.
well, really it's a 2 by 2 window, right? But, 1 away from the origin. Okay, not a huge deal, okay? So it looks like this. Right? It looks like, okay? And it kind of seems that, oh, dang it. That we kind of have an asymptote at 1. Don't you think that it looks like that? Like we have an asymptote at 1? Okay. Now, what we are going to use is the absolute value of x and negative absolute value of x. So, math is where you find the absolute value, math number, absolute value of x, and negative absolute value of x.
It's all squeezed.
Wait, so you want the absolute?
Are we making a spider web?
The negative absolute value of x. So we have,
I'm gonna go home.
I'll go to math.
okay? All right, so my calculator is showing a much better picture of what's actually happening, right?
Yeah.
Is our x sine of 1 over x squeezed in between these two functions?
Yes.
Yes, okay, and they are meeting up at 0, 0. So, what is the limit as x approaches 0 of the absolute value of x? Okay. What's the limit as x approaches 0 of negative absolute value of x?
0.
0. Since our function is sandwiched in between these two functions, then we can say the limit as x approaches 0 of x sine of 1 over x is also 0. That's how it works. Yes.
So if we didn't use this method, then, like before, like what you told us today, would we have said it doesn't exist, or would we?
We wouldn't have a way to find it.
Okay, so this is just a way to like give it a number.
Yes. Without having to necessarily look at the graph. What?
It's not, it's not, it's not.
That's what happens.
Okay, so there's the squeeze theorem. Like I said, we're not going to do much with it, but you need to know about it. All right? Let's talk about trigonometric functions. First of all, if you have a trigonometric limit where the function is purely trigonometric, you can use direct substitution as long as it's not an undefined value, right? Tangent, cotangent, secant, and cosecant, they have vertical asymptotes. Obviously, we're not going to have a limit where we have a vertical asymptote. We would say that doesn't exist, right? But Otherwise, we can just use direct substitution. So the limit as x approaches pi over 3 of secant of x just means we're going to take secant of pi over 3, and you all are masters at your unit circle. What is that?
Secant to absent of sine, cosine.
Reciprocal.
Reciprocal of, so I'm gonna go with
Secant's the reciprocal of what?
cosine.
Cosine.
Cosine of pi over 3 is. Okay.
The cosine of
Answer's 2.
pi over 3 is 1/2. So the secant is 2.
When I time myself in that minute circle, it was like 45 minutes.
Okay. Needs to be quicker. Let's try this. The limit as x approaches 5 pi over 6 of tangent of x, we're just going to evaluate the tangent of 5 pi over 6, and it is
Square root of 3. Square root of 3 over 3. It is negative.
negative second quadrant. Okay. You guys just got to remember your reference angle.
Hey, I was getting there.
If it's pi over 3, it's radical 3. If it's pi over 6, it's radical 3 over 3. Just remember it. Okay? Now. What? Was that too fast?
I didn't see anything.
Well, you usually do.
See, you got me there.
Okay, now we are not always going to have just a purely trigonometric function. Okay? We have two special trigonometric limits. Write them down, memorize them, know how to recognize them. First one, the limit as x approaches 0 of sine of x over x equals 1. Every time. Next, the limit as x approaches 0 of 1 minus cosine of x over x equals 0. Okay? Now, remember, we can take the limit of like a division of two functions. So, by saying the limit as x approaches 0 of sine of x over x equals 1 also means that if you have x over the sine of x,
It's 1.
it'll still be the same. Okay? So as long as you have sine of x over x or the reciprocal, it will still be this special limit. Okay? Yeah, I think you were right.
Yes.
Okay? If I change my mind, I will let you know. But I think that is right. Now, look at my first example. Mrs. Homan, that doesn't look like the special limit that you gave us.
But you can cancel out the 2's.
Oh, no. We can't cancel out the 2's. I can't take something out of the trig function. But is the angle the same as the denominator?
Yes.
That's all that matters. Here, the angle is x, the denominator is x. Here, the angle is 2x, the denominator is 2x. So this limit is still 1.
So
As long as the angle matches the denominator, that's all that matters. Okay? Please be able to recognize that.
Okay.
Now, we are going to use these special trigonometric limits to help us. First example, the tangent as x approaches 0 of tangent of x over x. Okay? We cannot use direct substitution because of that 0 in the denominator. You're not going to just say, does not exist. Okay, we need to try and see if we can make it work. Yes?
could you make an
we could make tangent sine over cosine.
Without the cosine. Oh my gosh.
Okay?
Is it for, okay, never mind.
Okay? Now, okay, that looks kind of funny, right?
But,
So can we use the squeeze theorem for that though? Because it would be at 0. And if you're using absolute value, it would approach.
Well, this is going to be a different graph, though.
Okay.
Okay? It only works because of the graph that we have. Okay? Now, let's rearrange this. The limit as x approaches 0, we're like multiplying by the reciprocal, right?
Yeah.
So you have the sine of x over cosine of x, careful, times 1 over x.
Oh, yeah.
You
Okay.
just do x
So
cosine.
can't you just multiply across and then it's still the same thing I just said?
No.
So now let me rearrange this again. The sine of x over x times 1 over cosine of x.
Oh, snap. What?
Okay? What happens to this? This limit goes to 1. Okay, that's just my notation to, hey, I know this limit is 1. Okay? And so now I have 1 times 1 over the cosine of 0,
Which is just, one.
which is 1.
How come you can split them apart like that?
Multiplication is commutative, right?
Yeah.
Okay? So I can multiply in different orders and it's still the same.
For some reason I feel like we've never done it that way.
Yeah.
Like that was
Oh.
mind blowing.
It's great.
Or just, imagine it like it's just one line. One line, you just have to, yeah, you got it.
Okay, all I did is I said x, cosine of x times x is the same thing as x times cosine of x. Right? That's all I did. Nothing too fancy.
This next one's gonna be fancy. You're so fancy.
This one, okay. What's the problem with trying to evaluate this limit with my special rule?
There's a
There's a
five.
They're
5.
different angles.
Oh, dang.
Okay, the angle is not the same as the denominator, is it? What would the denominator need to be for this to be special?
5
You.
5u. Okay.
So now it's the answer. Oh, multiply by 5 over 5.
Okay, we can't change the value, but we can multiply by a well-chosen one. What do I mean by a well-chosen one? I multiply by 5 over 5.
Fits the purpose
One.
that you want.
Right? We have not changed the value, but now this looks like 1/5, whoops, nope, not 1/5, 5 times the sine of 5u over 5u. And what's the limit as u approaches 0 of the sine of 5u over 5u? That goes to 1. And what's the limit as u approaches 0 of 5?
5.
So we have 5 times 1, which is
7.
Hey. So, if there's ever a coefficient up in the sign, it's just not going to be your answer.
Absolutely.
not necessarily.
No. Well, I mean, like if it's just the variable on the bottom, like there.
Okay, how about this? If your angle does not match your denominator, you're going to have to multiply by something to force it to be special. But I need to see all that work.
How special.
Okay? Let's try this one.
There you
It's just like don't make it look too scary.
Okay, we can't multiply by 5/3
go. Why not? Oh, 'cause it's not one.
because 5/3 is not multiplying by 1. Let's do this just a little bit at a time.
Let's do that.
Okay? If I wanted, okay, now first of all, we cannot do direct substitution because the sign of 0 is 0. Correct?
Good.
Okay, because that's always the first thing we should check. Can we do direct substitution? Okay, in this case, no, we can't. Now, what would our denominator need to be if I wanted a special limit with sine of 3 theta?
It should be sign of 3 theta.
We would need it to be over
3 theta.
3 theta. So let's multiply by 3 theta over 3 theta. Okay, I'm not changing the value, am I? Now, is everyone okay that I split apart my signs?
Yeah.
Okay, so now I'm just trying to be organized here, okay? So now I have the sine of 3 theta over 3 theta times 3 theta or sine of 5 theta, right?
Okay.
Okay, so what is this limit?
1.
That limit is 1. Okay. Okay.
Do we have to multiply that by 5 theta? It's pretty cool.
What do we need to multiply by now? Okay, so now let me just rewrite it. We have the limit as theta approaches 0 of 3 theta, okay, over sine 5 theta.
But that's still true.
Okay, so now what does our numerator need to be if I want a special limit with sine of 5 theta?
5 theta.
We need a 5 theta, right? Well, I already have a theta. So let's multiply by
5 over 3.
what?
5 over 5.
We can only multiply by 1.
5 thirds over 5 thirds.
Let's keep it simple. Let's do 5 over 5. Because watch what we can rearrange this to.
Fair enough.
I can say that I'm going to leave the 3 here. I'm going to group 5 and theta together
Okay.
over the sine of 5 theta.
That's tricky. I think this is breaking.
And I'm going to bring,
I know it's not, but I don't feel like it's fair to just separate 3
Right.
theta like that. Because I feel like they're
is it, but this is
They had such a good relationship.
3 times theta
Yeah,
times
I
5.
got you. I know
Now
it's
it's 3 times 5 times theta.
I was just confused.
So,
If you need to multiply by 5 theta over 5 theta, that is fine. Because the
But does that
thetas
make
will,
more work for
the
me?
thetas will cancel in the end.
Oh.
Okay, so if you need to do that,
It's weird. I suppose if it was as x instead of a theta, it would make more sense. Like my button is better.
okay. So is everyone okay with how I rearranged our fractions?
Sure.
Oh,
Yeah.
Who said sure?
Aaron.
Okay, is that a yes, sure?
Yeah.
Okay. So now, what's the limit as theta approaches 0 of sine of 5 theta over sine of 5 theta?
1.
That goes to 1, and we have the limit as theta approaches 0 of 3/5, which is
3/5.
3/5.
Yeah.
so the sine and theta just. Oh,
They're not going to cancel, no.
so that's where we use the reciprocal in this one.
Yes.
I would have worked.
Okay.
You don't care.
Yes, I know. If you want to do that, that's fine.
Okay.
Okay. I'm going to stick with integers. Okay? Okay. So, this is your homework.
That's it. Oh.
Yeah.
It's confusing. I dig it. Yes.